we just found a relationship that says that there is a magnetic field produced by current in a wire. So why isn't every wire, all the wiring in the house, why isn't the cable charging my laptop right now? Why isn't there a whole bunch of like magnetic interference with everything? And it is because cables and wiring put oppositely directed currents very close to each other. Change the direction of the current, again with the right-hand rule. If one current goes up, that makes a current or a magnetic field this way. If the other current goes down, that magnetic field tends to oppose the one created by the first current. So if we have current passing in one conductor one way and the other way in a nearby conductor, the net effect away from the wire is for there to be almost no magnetic field, which is good. Otherwise, there'd be magnetic interference all over the place. What do you think? What questions do you have at this point? Okay. Speaking of conductors carrying oppositely directed currents nearby each other, if a conductor carrying a current creates a magnetic field, we saw before break that a different current carrying conductor feels a force in an external magnetic field. Each of these conductors that we're talking about here is carrying a current which creates a magnetic field, and that magnetic field will cause there to be a force felt by the other conductor. So they're going to exert forces on each other mutually, which is pleasant from a symmetric, Newton's third law kind of sense. Each one creates a field. That field exerts a force on the other. How much force are we talking? Remember our cross product, force on a wire carrying a current I with a length L that passes in a magnetic field B. Now the whole story here is rectilinear. It's all perpendicular. So the cross product just gets us the magnitudes. The force is I, L, B. Force per unit length. So force divided by L gets us I times B. But B is the thing that we just found an answer for. Mu zero current divided by 2 pi and the perpendicular distance from one to the other. each feels the same magnitude, because the whole situation, you take the picture, turn it upside down, it should get you the same story, whether you look from I prime to I or from as pictured I to I prime. It's the same scenario. If I and I prime are in the same direction, the result has a positive polarity, positive sign, which we take to indicate attraction. If they have opposite directions, then there will be repulsion. The magnetic field of the lower wire, if they're carrying current in the same direction, exerts an attractive force on the upper wire, and vice versa. If the currents were traveling in opposite directions, there would be a repulsion. And again, we're sort of accounting for that by examining the positivity or negativity of this product. The product of the two currents, if it is positive, then the currents go in the same direction, and that is attraction. Okay. So far, so good. In fact, the force on two parallel conductors is the operational definition of an ampere of current. Because we define it the way that we do, mu 0 and 4 pi, or I guess 2 pi, showed up in that result for the magnetic field of a linear conductor. One ampere is the constant current that of two parallel conductors of infinite length, 1 meter apart in empty space, causes each one to experience a force of 2 times 10 to the negative seventh newtons per meter. That 2 is so that we can discuss 4 pi instead of 2 pi. And there's a 2 pi in this formula. But if mu 0, if we're defining it so that the force is 2, then the quotient there needs to have the value of 2. So we need mu 0 to be defined as exactly 4 pi times 10 to the negative seventh Tesla meter per amp, If it were not that, then our definition of an ampere would not make any sense. So we choose the value of the magnetic constant to make our definition of an ampere of current nice. Four pi times 10 to the negative seventh. Exact. Not to any precision. That's just, we just picked that. And the actual definition of a coulomb of charge is related to that. So it all comes back, it all actually comes back to magnetic fields for some reason. But we defined charge itself, the very first, fundamental piece of the electricity discussion. We actually define it in terms of an ampere, which is defined in terms of magnetic fields, which again sort of hints that there's an intimate connection between them.